you can derive the equation at the heart of quantum mechanics under 60 seconds. The Schrödinger equation is one of the most famous equations in quantum mechanics, appearing in solving the hydrogen atom, describing quantum superposition, quantum entanglement, and quantum tunneling. You can construct this equation by using one simple idea. Total energy equals to the Hamiltonian, and that's it. And let's begin with something that everybody knows, conservation of energy. So the total energy is nothing but the kinetic energy plus the potential energy. And the kinetic energy, we know that 1/2 mv squared, and we can express this in terms of momentum, which is nothing but the mass times the velocity. Nothing here is quantum yet, just basic physics. But here is the leap. In quantum mechanics, we operate within the framework of canonical quantization, meaning that classical variables like position and momentum are promoted into mathematical operators that obey specific commutation relations. Due to the uncertainty principle, the position and the momentum are complementary observables. They cannot be simultaneously specified with arbitrary precision. Rather than treating momentum as a classical variable, we promote it to an operator, an observable whose eigenvalues correspond to measurable momentum values. The correspondence principle tells us that the classical observables must map to Hermitian operators in quantum theory, and through canonical quantization we identify the momentum operator with the minus the complex number reduced Planck constant times the gradient, and this is the momentum operator in the position representation. It generates spatial translations as a consequence of translational symmetry via the Noether's theorem. The gradient encodes the spatial derivative action on the wave function psi. When this operator acts on an eigenstate of momentum, it returns the momentum eigenvalue. So rather than asking what is momentum, we ask what is the expectation value, and this is precisely what the operator formalism provides. Now apply the substitution to energy conservation. So the classical is p squared over 2m plus v, and then we promote the operator. Here is our momentum operator. Then we substitute minus I h bar the gradient, and then we obtain this energy operator. And then we apply this energy operator on the wave function. Hamiltonian on the wave function gives you the energy eigenvalue times the wave function. Now we can connect energy to time evolution, and this is where quantum mechanics becomes elegant. In classical mechanics, if the Hamiltonian doesn't explicitly depend on time, energy is conserved. In quantum mechanics, we express this through the time evolution operator. And here x means the exponential, so e to the power. So this time evolution operator advances the quantum state from t equals 0 to an arbitrary t. So the Hamiltonian generates a temporal translation. If you shift time by infinitesimal delta t, the wave function changes by delta psi. And if you reorder this equation, you obtain something that resembles to some part of the Schrödinger equation. From this generator relationship, we immediately obtain I h bar, the temporal derivative of the wave function, is the Hamiltonian times the wave function. If you rearrange your equation, you obtain the following, and this is the Schrödinger equation. If this ignites your curiosity, subscribe to Breaking Space Time, and I will see you in the next one.